Let us apply these formulations to an example. Let's consider air that is compressed from initial pressure and temperature of 1 bar and 20 degrees centigrade respectively to a final pressure of 5 bar in a reversible process. We want to determine the work and heat transfer per unit mass and change of entropy if our polytropic index is known as 1.3. We want to also consider this when our process is isentropic. We will use EES to solve for this. To use EES, we will first define constants. R, our gas constant, is 0.287 kJ per kgK. In our first instance, N is equal to 1.3, which is not equal to K for air, which is taken as 1.4. At state 1, we know our pressure to be 100 kPa, and we know our temperature to be 293.15 Kelvin. Thus, at state 1, our specific internal energy is an energy of air taken at T1, and our specific entropy, S1, is equal to entropy of air taken at T1 and P1. At state 2, our pressure has increased to 500 kPa, and our temperature can be found using our polytropic expressions. That is, T2 is equal to T1 times P2 per P1 to the quantity n minus 1 per n. U2 is our specific internal energy taken at state 2, and S2 is our specific entropy taken at state 2. Our work going from state 1 to state 2 on a per mass basis is our gas constant times the quantity T2 minus T1 per the quantity 1 minus n. Our heat input, Q going from state 1 to state 2, is a change of our internal energy between state 2 and state 1 plus our work, and we'll calculate our change of entropy between our final initial state as a check. Now let us evaluate this for when n is equal to 1.3. We know 1.3 is not equal to 1.4, therefore this process is not isentropic and we expect a change of entropy. When we do our calculations, we see our work supplied going from state 1 to state 2 is minus 126.1 kJ per kg. That is, we have work into our system. Our heat input is minus 30.89 kJ per kg. That is, we are rejecting heat. And our change of entropy is minus 0.08734 kJ per kgK. That is, we have a decrease of entropy within our system. Now, if we look at our state variables, we can see that during this process, our temperature has increased 425 Kelvin during this compression process. Now, if we set n is equal to 1.4, that is, we have an isentropic process, and recalculate our system properties. We see our work going from state 1 to state 2 is 122.8 kJ per kg, negative. That is, we have work into our system. Our heat going from state 1 to state 2 is 1.242 kJ per kg. This is very close to 0. Also, we see that our change of entropy is equal to 0.002662 kJ per kgK. This is also very close to 0, and this is within round-off error of the calculation. We see that if we calculate our system properties, our temperature has increased to 464.3 Kelvin. That is because we have no heat rejection. For it to be isentropic, it has to be reversible and adiabatic. And we saw our heat supplied is near 0 within our round-off of our calculation. Now, it is suggested that you consult the supplemental slides that go through the calculation by hand, not using EES, for when n is equal to 1.3, and also for when n is equal to 1.4. These are found at the end of the slide deck corresponding to lecture 21.